Hello and welcome back to some more organic chemistry reactions. Today we will be covering ketones and aldehyde reactions. We're going to look at the many different types of reactions we can do with ketones and aldehydes. But specifically, let's just stick to nucleophilic addition, something that's very unique to ketones and aldehydes. Now, you might have seen already nucleophilic addition in the past, but just in a different way. Now, what reactions could that be? Well, we have our Grignard reaction. If we have some sort of alkyl group represented by R, we have our magnesium and X, which represents a halide. This Grignard reagent can basically attack the carbon that is connected to the oxygen, which is basically our carbonyl group over here. It can do it for both the ketone and the aldehyde in the same way. And they both result the same product, it's just one's more substituted than the other. In the ketone case scenario, we have our oxygen. Let me draw that a little bit better. We have our oxygen that has a negative charge and paired up with a magnesium with a positive charge. It still has its alkyl groups and now has an R group. And as for the aldehyde, it's now the same thing, oxygen with a negative charge paired up with a magnesium with a positive charge. And we have our other R group that's been added by our Grignard reagent. Now, for our ketone, we can also add some acid to it, and this will just turn it into a tertiary alcohol. So right here, we have an OH group. Now, as for our aldehyde, we can do two things. We have, well, let's just label this tertiary alcohol. Much better. Now, for the aldehyde, we can do either two things. Either we can add acid, and just like with the ketone, we would get an alcohol, but rather this time it will be a secondary alcohol. And we can also do something else. We can also, after we add this acid, we can oxidize it. And if we oxidize it, what ends up happening is now we get a ketone. So notice how the aldehyde, since this carbonyl group is only monosubstituted, once you add that Grignard reagent and add an alkyl group, now it's disubstituted, and if you oxidize that alcohol group, it becomes a ketone. So that is one of our nucleophilic additions, and this adding of the acid and oxidizing not the nucleophilic addition, but rather the Grignard reaction itself is. Now, another type of nucleophilic addition is with an acetylide ion. And notice how both the Grignard reagent and the acetylide ion are both really strong nucleophiles. They don't really require a catalyst for this to work. Simply, what happens is that we have our negative charge attacks the carbonyl group directly, just like in the Grignard reagent. And after we add some acid to add the hydrogen to the oxygen on these groups, either the ketone or the aldehyde, we get this product for the ketone. We still have our two alkyl groups. Now we have the acetal group, or the alkyne group, I guess, and we have our alcohol there. That's still a tertiary alcohol. And for our aldehyde, we have over here the alcohol group, and then now we have the alkyne group. And this is our secondary alcohol. And we have one more other reaction that's very similar to this that requires a strong nucleophile, and that is a nitrile group, which is basically a carbon triple bonded to another nitrogen instead of a carbon triple bonded to another carbon. And this can go either of two ways. Well, for both the ketone and the aldehyde, they will result in the same product. It's just one is more substituted than the other. So for the ketone product, after we have the potassium cyanide, which will act as a nucleophile, this hydrogen cyanide will provide the hydrogen for the oxygen in order to protonate them, and we get this product for our ketone, nitrogen. And as for the aldehyde, we have this product, an OH group, and then triple bond to a nitrogen. Now, we can stop right here, but nitriles have something very interesting to them. If you add acid to a nitrile, so say we do this reaction right here, so we're already done with our nucleophilic addition, but if you add an acid to this nitrile, we can get a really interesting product. We can get, for the ketone, we get this right here. I'm going to draw my alkyl groups. These two are still here. We have our OH group is still here. And then now, instead of a nitrile, this carbon group, instead of being connected to a nitrogen with triple bond, it's now a carboxylic acid. And the same thing with the aldehyde, our OH group. And now this carbon is made into a carboxylic acid. And so what this is called is an alpha hydroxy acid. And the reason it's called that is because the alpha carbon is the carbon right next to this carboxylic acid. That's why it's called an alpha hydroxy acid. Now, sometimes we don't really have strong nucleophiles. Sometimes we have weak nucleophiles. And what would we do in that scenario? Well, we got to catalyze them. So for this first case scenario, you have water. Now, if we have an acid, such as this proton right here, these electron pair, like these lone pairs right here on either the ketone or the aldehyde, they're very attracted to it. They're very likely to try and attack this proton. And after they attack that proton, essentially now we have an oxygen connected to a hydrogen, and that gives it a positive formal charge. And so it makes the carbon that's connected to the oxygen, the carbonyl group, have an even stronger partial positive at that carbon group. And it makes it a lot easier for the water to attack it. And so for the ketone, after the water attacks either the ketone or attacks the aldehyde, we get these two products. For the ketone, we now have the OH group, which was originally our carbonyl group, and now our new OH group that we added because of the water after it gets deprotonated. And then for the aldehyde, we have our OH group, which used to be the carbonyl, and another OH group, and this came from the water after it became deprotonated. Now, this is nucleophilic under acidic conditions. Now, if it's under basic conditions, it's very similar to how we had our Grignard reaction with either the acetylide ion or the nitrile. It's basically the same thing. It's just now we have our OH group from the sodium hydroxide essentially attack the ketone here or the aldehyde, and we don't need a catalyst to do this, and it's just diluted with water, and we just get these same products that we had with the acid catalyzed reaction. So that's the product for the ketone, and over here is the product for the aldehyde. Now, one more thing we can do. Now, say instead of water, we had a different scenario. Instead of just water, we had some, an alcohol, some other group. So, what happens is instead of water, we have an R group over here, which makes this an alcohol. Well, we can consider the first scenario. Either is it in acidic conditions or basic conditions. Well, if it's in acidic conditions, know that we have a proton over here, and the electron pairs on the ketone and the aldehyde are very attracted to it. And so they're very likely to just attack this proton right here. And what ends up happening is that it becomes an easy target for this OH group. And so we have our first step, which gives us an OH group here, the OR group, and then the rest of our alkyl groups are the same spot. And same thing for the aldehyde. Over here, an OH group, an OR group, and the same thing. Now, if we add even more acid, what ends up happening is now this OH group will get protonated. This will get protonated, and this will become protonated. And they'll become easy or great leaving groups because now they have a positive charge on them, and if they leave, they become a water molecule. And so another molecule of our OH group, or the alcohol, will come in and attack it again, and this will complete its reaction and become this final product. And this final product does have a special name to it. So same thing for the aldehyde, an OR group, OR group. This is called our acetal. So this is an acetal group. And this is basically the same thing as what we had over here when we had water. Here, in this case scenario, it's called the hydrate. Oh, my bad over here. This is called the hydrate of our molecule. This right here is an acetal. It's basically when we have a carbon connected to two oxygens, and those two oxygens are connected to R groups. Now, if we have basic conditions, what happens over here? Well, for the first reaction, we just have the R group, say that we don't have an H over here. This R alcohol, say it was deprotonated, it makes it a strong base, right? Or a strong nucleophile. It will proceed with the first reaction. So for the ketone, we have the OH group and an OR group. And then for the aldehyde, same thing, OH group, OR group. Now notice, since it's not in acidic conditions, we cannot further this reaction. Over here, these alcohol groups cannot be removed. We don't have an acid to make them good leaving groups. And so it stops right there. And what they call that is a hemi-acetal, or half acetal, essentially. It's basically only halfway through. Now, an interesting thing about acetals is that they can work as protecting groups for aldehydes. Why is that the case? Well, let's look at this molecule right here. Let's move it out of the way and give it some more space. Say we have this molecule right here, where we have both a ketone and an aldehyde connected on the same chain. Aldehydes, since there's less of an electron donating group around it, over here we only have one carbon being electron donating to that carbon with the oxygen, the carbonyl group, while in a ketone you have two carbons. So an aldehyde, being less stable, is more likely to undergo that acetal transformation. So if we have the same molecule right here, we have basically our glycol over here. We have two oxygens and hydrogens on them, obviously. If we add this to our aldehyde under acidic conditions, knowing that we have a dilute acid, what we end up getting is this right here. We have our ketone is actually untouched because it's less reactive than our aldehyde, and what our aldehyde transforms into is our acetal. And so we have our two oxygen groups, and they're both connected to that R group that's connected as a chain. And now we have this sort of cyclic structure. Now what's cool about this? This acetal group can act as a protecting group. So acetal is a protecting group over here. Just like how we had with our alcohol reactions when we used TIPS chloride to protect our alcohol group from Grignard reagents. It's the same case scenario over here. If say we had an aldehyde on the same molecule, instead of having a ketone, we had, a bromine, and we want to make that a Grignard reagent. Well, we have to protect our aldehyde group first, or maybe even a ketone group, before we proceed with that. And so this acetal, in the presence of both a ketone and aldehyde, will attack the aldehyde only first and create this sort of protecting group where we can actually, whether we can oxidize this, ketone, even rather reduce it, not oxidize it, or we can do some sort of Grignard reagent, so Grignard reaction. We can do all kinds of things with this ketone. Meanwhile, this aldehyde is protected as an acetal group. And the way to get rid of this is just to add some acid. Add some acid, and this goes back to our product over here. It goes back to the way it was after with whatever modifications we made. And so this acetal group is really interesting. So that's it for now. In our next video, we will be covering the further reactions of ketones, such as reductions and other special reactions to test for aldehydes as well.